Welcome everybody to chemistry. This is our first lesson of the year. This is going to cover Chapter 1, Section 2. So Chapter 1, Section 2, we're going to look at matter and its properties. Just to start off with, you're going to see several different messages as we go along, not messages, but different patterns as we go along the way. And what I'm highlighting here is most of the definitions will start off with a yellow word and the definition is right behind it. Please, please, please write down every definition in your notes. I might say the definitions, but you'll need to pause the video, write those down, and then move on with the video so that I can make a shorter video. So starting off, we've got three definitions: volume, mass, and matter. Volume is the amount of three-dimensional space an object occupies. Mass is the measure of the amount of matter, and matter is anything that has mass and takes up space. So in other words, matter is anything that has mass and has volume. Mass and volume. Please write those down. If we're looking at the basic building blocks of matter, you have three more definitions you need to write down for atom, element, and compound, and these will get discussed further throughout the lesson. But an atom is the smallest unit of an element. An element is a pure substance that cannot be broken down into simpler, more stable substances. So again, it is a pure substance. Pure substances will be brought up later that cannot be broken down. And then a compound is a substance that can be broken down. It can be broken down into simpler substances. And for a compound, you do have two or more elements that are chemically bonded. Here's an example of an element on the left. You've got your carbon, and it's multiple atoms. They're showing that as the green structure there, multiple atoms that are bonded together. And on the right, you've got a picture of a compound with hydrogen, oxygen, and carbon, multiple atoms again put together to show you what a compound looks like. Moving on to types of properties. We're going to look at two types of properties in this section: extensive and intensive properties. So for our extensive properties, again, another definition for you. It depends on the amount of matter that is present. And the key to this definition is it depends on amount, or how much of your substance do you have. Some examples of extensive properties are going to be volume, mass, and amount of energy in a substance. So again, volume does measure an amount. If you think about a 2-liter Coke or a gallon of milk, it does tell you how much you have of that substance. Mass, if a penny is 5 grams, that is the mass of it. Tells you how much copper that you have for your penny. And then, of course, your energy is another example. So those are extensive properties. If I'm looking at intensive properties do not depend on the amount of matter present. Another way to look at this, intensive starts with the letter I. So intensive properties depend on the identity of your substance. So intensive properties depend on the identity of your substance. How do you identify it? But it does not depend on amount. Some examples of intensive properties are melting and boiling points of a substance, density, can it conduct electricity, can it transfer energy as heat. So any of these would be intensive properties. An example of this would be, let's say that you had a cup of, let me go back here. Let's say that you had a cup of water. Well, that 1 cup of water will boil at 100 degrees Celsius all day long. If you had a large, sorry about that. If you had a gallon of water, that is also going to boil at 100 degrees Fahrenheit. So again, it doesn't matter how much water you have. We all know water, which we're familiar with, and you'll hear me use water as examples all of the time because of the familiarity. Water boils at 100 degrees Fahrenheit. Does not matter how much you have of it. So as we're looking at this right here, and it's giving you a description and example, two more that I want to bring your attention to are going to be malleability and ductility. We use those words often whenever we're talking about different metals, but malleability, ability to be hammered or beaten into thin sheets. So I'm thinking of aluminum foil. You'll probably have some of that at home. And then ductility, ability to be drawn into a thin wire. My example there is you're probably used to seeing copper wire. That's what we use to run electricity in our homes. Both of those are going to be intensive properties because it depends on the identity of your substance, not how much you have. A 1-inch piece of copper wire is going to conduct electricity. Again, there it is, conduct electricity just as well as 100 feet of copper wire. The ductility of it doesn't matter how much you have, you still have the ability to draw it into a thin wire. So all of these are examples of intensive properties. So we just finished up looking at intensive and extensive properties. Now we're going to move on to the physical side of this, and we're going to look at physical properties and changes. You've got two definitions that you need to write down here. So for physical property, a physical property can be observed without changing the identity of a substance. Can be observed without changing the identity of a substance. So no identity change. Whereas a physical change also does not involve a change in the identity of your substance. Both of these sound very similar as far as their definitions go, but the key to both is going to be we're not going to change the identity, but we can still study that substance without changing its identity. So if I want to look at the boiling point of water, not a big deal. The boiling point, I can boil the water, and as long as I trap all of the steam molecules and just let it set, it'll go right back to liquid water. I never changed the fact that it was water. Cutting, that's a physical change. That's really easy. If I take a piece of chalk and I break that piece of chalk in half, now I have two pieces of chalk. Both of them would write on a chalkboard just the same. They're just smaller now. So physical properties and changes will not change the identity of your substance while you are observing those. I like to say another big one right here. If I'm looking at the melting and boiling points of a substance, with these, I like to group my phase changes or changes of state into here too. So you'll see these phase changes very often. And again, with these phase changes, also called changes of state, and I abbreviate a lot, that's going to be looking at a solid to a liquid, liquid to a gas back to a liquid, liquid to solid, solid straight to a gas. I think you get the idea, and we'll look at that some more. But phase changes, you can go through a phase change with liquid water. It's still H2O, no matter what phase or change of state it is going to be in. So here we've got some more definitions. So there's your change of state. It is a physical change. The states of matter we're going to look at are solid, liquid, and gas states. Plasma, we won't talk too much about plasma in this particular class. But going back, solid state, you need to know the difference between your different states. Get these definitions down. You're going to do some drawings here in just a little bit. But for our solid state, a solid has a definite volume and a definite shape. So they are fixed. The word definite means fixed, stays the same. So if you're studying something in the solid state, those are going to be in a fixed state. Liquid state has a definite volume but an indefinite shape. So another word for indefinite is going to be variable. That means the shape can change. If you've got water in your water bottle, not a big deal. The water can sit there and freely move around inside of the bottle, but we're not going to lose any of the volume of the water as long as that lid is tight on there. And then the gas state, with this one right here, it has neither a definite volume nor a definite shape. If you had gas contained within a container, but as soon as you take that lid off, the gas molecules are going to be free to move outside of the container too, and it has to do with them being in a constant motion. And then get down the definition for plasma. Here we go with our first animation. We're going to look at solid, liquid, and gas. And as you're watching this, take some notes if they're not already included. And I will have you redraw in your notes the top part of this video.
Solid has definite volume and definite shape. The particles of a solid vibrate in fixed positions and are held in place by strong, attractive forces between them. A liquid has a definite volume but not a definite shape. The particles of a liquid have a range of movement that allows them to slide past one another. A gas does not have a definite volume or shape. The particles of a gas move fast enough to overcome nearly all of the attractive forces between them. Gas particles move independently of one another.
So as you're looking at this and you're trying to figure out what to draw, do your best rendition of the drawings that are here at the top for the solid, liquid, and gas. Moving on, so we just finished up our physical properties and physical changes. Now we're moving to chemical properties and chemical changes. And again, the definitions for these two are going to be very similar, and that both of these, when you're studying them, you will undergo some type of identity change or some type of transformation. For a chemical property, it is the ability to undergo changes that transform it into a different substance. So there is an identity change. There is an identity change. And for a chemical change, you are converting one substance into a different substance. Convert means to change. So you've got one or more substances are converted into different substances. Again, an identity change are chemical reactions that we will talk about go underneath these chemical changes. Get those definitions. We're going to look at an example of a chemical reaction now, and we're going to see if you can't pick out some things that are going on to say, oh, a chemical reaction is definitely taking place.
When liquid bromine is added to aluminum foil, the two substances react. Heat and light are indications of a chemical reaction. Aluminum bromide is produced and deposited onto a cooler surface.
So if I'm looking at this video, I can tell for sure there's a couple things going on to say, yep, I definitely got some different substances to show a chemical reaction. We started off with a piece of aluminum foil, which is silver, and now I'm left with some type of white powder that's in there. You could also see steam being given off, so some type of gas was being given off within all of this, even though you started with a liquid bromine, which was that brown substance, and your solid aluminum foil, which was the silver one. So we had a chemical reaction going on with this. If I were to look at just a formula to kind of go with this, we had aluminum, now that you're studying some of your elements, bromine. You'll learn later on why I'm putting the little 2 down there, but they put aluminum and bromine together. That arrow says it created something, and it created. That formula stands for aluminum bromide, and that is that white residue that you see left in the beaker. Moving on with a couple other words you need to know for the chemical reaction we just looked at. So I had written down the reactants and the products of that particular reaction. Make sure you write down the definitions for these. So a reactant is always going to be on the left side of that arrow. It is the substances or substance that you react with something else to start off your chemical change, and the products, they are what are formed or what comes to the right of the arrow. In the example here, they're saying carbon plus oxygen yields carbon dioxide. So there you've got your carbon, and again, if I put a symbol to it, that is your C, plus oxygen, that's your O. Again, this one's going to have a little 2. You'll learn why later. Yields carbon dioxide. The formula for it is CO2. So my reactants are going to be carbon and oxygen. It's the substances that are reacting with each other. And then my product in this case, which there is only one, is the carbon dioxide. Looking at evidence of a chemical change, and you need to write down all 4 of these. In general, number 1, the example they give is acetic acid and vinegar and sodium hydrogen carbonate or baking soda being put together and a gas forms. If you've ever made any of those homemade volcanoes at home, or maybe it's some type of science function, then you have seen those put together. So a gas released is going to be evidence of a chemical change. That's the first one. The second one is a precipitate forms. Precipitate sounds like what it's doing outside right now, actually. Precipitation, falling out. This one, though, it is key. It is when you have 2 liquids put together and they form a solid. That is unusual, but it happens. So 2 liquids come together, form a solid. That solid is a precipitate. This third one that you see is the release of heat and or light. If you've ever seen fireworks, yep, there's a chemical change going on there. And with the last one, most of the time, if there is a color change, then a chemical reaction is taken place. Again, most of the time, a color change, a chemical reaction is taken place. Please make sure you get all 4 of these evidences written down. Here's another example. We've got electrolysis. Electrolysis is a special word that we usually talk about when we're talking about trying to separate out water, but you pass electricity through water, and water is then broken down into hydrogen and oxygen gases. And in this setup, even though it's liquid water, when you break it down, the hydrogen and oxygen gas, or hydrogen and oxygen, will separate out into their gas form, and that is what is going to be collected on each side of there. So that is a process called electrolysis. Here's another example where they are taking mercury 2 oxide, that is that brownish red substance that is in the test tube, and they are heating it up. When they heat it up, the mercury 2 oxide compound breaks down into oxygen gas and solid mercury. So oxygen gas will release up the test tube. That mercury is a silver gray substance. That's what looks like is being deposited on the inside of the test tube on up. But you can see evidence of a chemical change. Gas is given off. That's your oxygen. And a color change. So that brownish red color changing into that dull gray color. Definitely a couple evidences of a chemical change. Now we're going to compare physical and chemical properties. Remember, physical, there is no identity change, whereas a chemical property, there will be an identity change.
The ability of an iron nail to be bent is a physical property called malleability. The rusting of iron is a chemical change. Iron's reactivity with oxygen to form rust is a chemical property. The food coloring in this water is red. Color is a physical property. Adding bleach to the solution changes the chemical composition of the dye, and it is no longer red. The ability of bleach to make other substances colorless is a chemical property.
So you know as well as I do, if you add bleach or get a spot of bleach on your clothes, it is going to stain your clothes or dye it. You'll have a white spot, hopefully not too big, and you're not going to get that color back. The same with a rusted nail. Once it starts to rust, they say knock the rust off, but you cannot get that part of the nail back because of the chemical reaction that has taken place. With the nail, it's still a nail. It's just in a different shape. Maybe you straighten it back out, use it, and you're good to go. So know the difference between chemical and physical properties. Now we're going to look at the difference between chemical and physical changes.
Breaking a piece of chalk in 2 or more pieces is an example of a physical change. Regardless of how many times the chalk is broken, it is still chalk. The physical properties of size and shape are altered, but the chemical properties of the chalk remain the same. An example of a chemical change is baking a cake. When baking a cake, eggs, flour, sugar, oil, and other ingredients are combined. Each ingredient has its own set of properties. If the ingredients are mixed together and baked, something completely different is created. The heat from the oven and the interaction of the cake ingredients cause a chemical change.
So this is going to round out basically this initial part talking about your physical chemical changes, physical chemical properties, intensive, extensive properties, and just knowing that, hey, with all of this that we've talked about, energy is always involved in any of these changes. If you've heard of the law of conservation of energy, that is essentially what we're talking about there. Energy comes in various forms. When we're talking about chemical and physical reactions, we are saying typically heat and light are going to be involved in these, not always. But make sure you know the law of conservation of energy, and it is highlighted right here at the bottom. Get that definition in your notes. Now we're going to transition over to classification of matter. And you have a nice big flow chart right here. We're going to add to it as we go. But for your classification of matter, we're going to start at the top with matter. Matter is anything that has mass and takes up space or has mass and volume. The first question you have to ask yourself, and we're going to lead ourselves over to the left side of this, is can matter be separated? If your answer is yes, and when we talk about separation, we are talking about a physical separation. Can it be physically separated? Then what does that look like? Let's go give you some examples of what is ways in which you can physically separate something. Here are 3 examples of physical separation. There on the left we have filtration. So if you've ever made a pot of coffee and you don't want the coffee grounds within the liquid part that you're drinking, you filter it. In the middle, that device is a centrifuge. Newer ones look a little bit different. Centrifuge, really common in labs at doctors' offices. If they want to separate out your blood into the plasma and then the other part of your blood, the red blood cells, they will spin it very, very fast to get that separation. And on the right, that is paper chromatography. Very common to use paper chromatography as a means to separate out inks into the different colors that make them up. So for instance, if you had a green pen and you wanted to know what colors were in it, you can make a small dot, go through paper chromatography, and you're probably going to get bands of yellow and blue, maybe some other colors, but definitely yellow and blue that are going to make up that green tone that you're used to seeing. So heading back over here, can it be physically separated? Those aren't the only 3 ways, but if you answered yes, it can be physically separated, then you have a classification called mixtures, and you'll get these definitions here pretty soon. Mixtures, they're going to be a blend of 2 or more kinds of matter that have their own properties and their own identity, and they can typically be separated. So if your matter can be separated, you have a mixture. And then you ask yourself, well, is the composition uniform? Does it look the same throughout? If you answer yes, I feel like it looks the same throughout, Then you have what is called a homogeneous mixture, and the prefix homo means one or uniform. Some examples are going to be air, sugar water, stainless steel, and in some of your work later you'll get to figure out some other types of homogeneous mixtures. If your composition of your mixture is not uniform, then you have a heterogeneous mixture, and again that prefix hetero typically means two or more. And granite, if you have granite countertops at home, think of a big rock. Rocks don't really look uniform. Wood is an example of a heterogeneous mixture. Blood is an example of a heterogeneous mixture. We just talked about centrifuging blood and separating out the plasma from the red blood cells. So that is also going to fall better under heterogeneous instead of homogeneous. Heading to the other side of our flow chart. So now, as I'm looking at this and we're saying, can it be physically separated? If your answer is no, it cannot be physically separated, you have a classification of pure substances. Pure substances. From your pure substances, you ask yourself, well, can my pure substance be broken down or decomposed by ordinary chemical means? So can it be chemically separated? Chemically separated is probably going to involve heat and or light or electricity. So heat, light, electricity typically bring about chemical separations. If it can be chemically separated, then you have a compound. Water, sodium chloride, sucrose. Pretty much for our compounds, if you can write a formula with it. Water, you know, is H2O, I hope. Sodium chloride, that's table salt, NaCl. Sucrose is a form of sugar, so we're going to write down one of our sugars here. C6H12O6. There's several types of sugar: sucrose, fructose, glucose. But with each of these, if it's a compound, I can write a formula for it. Can you write a formula for air? Nope. We have lots of things in air. We've got a lot of nitrogen, oxygen, but you also have other impurities: carbon monoxide, carbon dioxide, and other gases. With these, you're going to have that. Another compound that you're familiar with, carbon dioxide, CO2. See, I wrote a formula for it. Going back up, if my pure substance cannot be broken down chemically, so it doesn't matter if you put electricity to it, heat to it, water to it, all of these normal means, you're not going to get it to break down. In this case, we have pure elements. So your gold, aluminum, oxygen, chlorine, it's those elements that you're studying off the periodic table right now. Gold, its symbol is Au, aluminum, Al, chlorine, Cl. And hopefully you can look at the periodic table, name about 118 of those. Those are your elements that cannot be physically or chemically broken down, and they are also classified as a pure substance. So your main four types of matter we're going to look at homogeneous and heterogeneous mixtures, and then we're also going to be looking at compounds and elements, which are your pure substances. Please get this flow chart and all the details in your notes. We're finally putting some definitions to what we saw in our classification flow chart. For a mixture, it is a blend of two or more kinds of matter. They have their own identity. They are mixed together physically. That is important. So mixed together physically and can be separated typically. Homogeneous and heterogeneous mixtures are the two types we looked at. Homogeneous mixture, it is very common for them to also be called solutions if they are in liquid form. So if you had a salt water mixture, you're going to call it a solution of salt water. And then heterogeneous mixtures, they are not uniform throughout. And again, if you had, say, sand and water mixed together, you know the sand is going to settle to the bottom. It is not uniform. So you have two examples here. On the left, you have your sugar water. You've mixed sugar and water together before. You know that sugar typically dissolves in it. Looks very uniform, but on the right, they're taking sand and water. It is not wanting to mix. For pure substances, there's your definition for it. Has a fixed composition. Our elements and compounds are pure substances. And here's how they differ from your mixtures. A pure substance will have exactly the same characteristic properties. So it does not matter if I have, we said water is a pure substance. H2O is its formula. If I have a cup of water or a room full of water, the properties are the same. Every sample also has the same composition, so water is always going to be H2O. Every molecule is H2O. And again, for the example for water, it's always 11.2% hydrogen, 88% oxygen by mass. By mass. So you would have to look at your periodic table to try to do some mass calculations. And to round it out, here's just a few more examples of homogeneous and heterogeneous mixtures. Again, homogeneous, we are thinking of things that are going to look uniform throughout. So uniform here, not uniform at the bottom. Iced tea, stainless steel, maple syrup, all of those look pretty uniform. But your orange juice, chocolate chip cookies, granite, which is like rocks, things in your salad are heterogeneous because they are not uniform.